thermodynamics. ओके, सो लास्ट टाइम हमने ये देखा था थर्मोडायनामिक्स के अंदर जो अलग अलग प्रोसेस होते हैं, तो उन अलग अलग प्रोसेसेस का डिटेल इंफॉर्मेशन देखा था। हर एक प्रोसेस के अंदर जो वर्क डन किया जाता है, तो उनके फॉर्मूलेस वगैरह भी हमने देखे थे सब। तो अभी आज के लेक्चर में हम उसके आगे जाएंगे। तो उसमें देखेंगे कि जो कोएफिशिएंट ऑफ परफॉर्मेंस ऑफ अ रेफ्रिजरेटर एंड द कोएफिशिएंट ऑफ thermal conduct coefficient of performance of refrigerator and also the efficiency of a heat engine, ये दोनों चीजें हम देखेंगे। And both of these are connected with the second law of thermodynamics. What does this second law of thermodynamics tells us is, so it simply tells us that the heat, the work done can be converted completely into the heat, but heat can never be converted fully into work done or mechanical energy. That is the second law of thermodynamics. Whenever the some amount of heat is getting converted into the work done, some amount of heat always just gets lost, and that lost part is also called as the entropy. Or lost means in the sense it is converted into such a form which is not never useful again, or it cannot be converted into any another form. And that will be called as the entropy. Entropy is the measure of unusable form of energy in the universe, and that's why efficiency comes into play. What does it mean, efficiency? Whatever amount of heat is converted into work done successfully upon the total amount of heat supplied to the system is called as the efficiency of that machine or any engine. So, and if we multiply it by 100, then we can get it as a percentage efficiency. Remember, so efficiency of a heat engine. अभी heat engine का structure कैसे होता है वो हमको पता होना चाहिए। heat engine suppose ये है, तो heat engine का काम ये होता है, it extracts the amount of heat from the source which is at higher temperature, let us suppose T1. so T1 temperature पे रहने वाले source में से ये Q1 इतना amount of heat absorb करता है, खींचता है, and out of that it converts some of its part into the work done. okay, successfully वो work done के अंदर convert करता है इसमें से, और बचा हुआ जो part है तो वो Q2 हम बोल सकते हैं, and that is actually rejected to the surroundings which is going to be at low temperature, that is T2. so we can say that this this heat engine extracts Q1 amount of part from the source, converts W amount of work done to convert a part of W in the work done through it, and rejects the remaining part Q2 to the surroundings. That means Q1 is going to be converted into two parts. One part goes to the work done and remaining part becomes the Q2, and that is going to be the entropy here. This Q2 is going to be the entropy, which is the unusable form of energy here. And that's why we can write the equation, that is Q1 is equal to W plus Q2. Okay, and hence we can call this W actually equal to Q1 minus Q2. And if you put this value of W here, then we get another formula for efficiency of a heat engine to be simply Q1 minus Q2 upon W. This is called as the formula for efficiency in case of a heat engine. Remember, तो heat engine का के बारे में हम बात कर रहे हैं यहाँ पे. Yes, and then again we can see, sorry, W नहीं, Q1 will be the original or input here with respect to which we want to compare this W. So W upon Q1 ये formula होगा efficiency के लिए, where we can just replace this W by Q1 minus Q2, and that is to be divided by Q1. This is again another formula for efficiency. Here we have to note that efficiency is always going to be less than 1. Okay, it's never going to be greater than 1. Greater than तो छोड़ो, equal भी नहीं हो सकता है. That is again another statement of second law of thermodynamics. And also one more formula for efficiency is simply Q1 and Q2 are to be replaced by T1 and T2, so that we get this T1 minus T2 upon T2, where T1 is the temperature of the source, okay, and T2 is going to be the temperature of the sink, you can see, और सराउंडिंग्स एंड ये जो इंजन का जो सोर्स है, सोर्स का टेम्परेचर एक्चुअली T1 है, और सिंक का जो टेम्परेचर है, मतलब सराउंडिंग का जो टेम्परेचर है, वो T2 है. इसको हम ऐसा भी लिख सकते हैं आराम से 1 माइनस, सॉरी, it will be actually T1 upon T2 minus 1. Sorry. Denominator में T1 Q1 है ना, तो Q1 should be replaced by T1 here, and hence we can get this as 1 minus T2 upon T1. This is actually going to be the formula for efficiency of a heat engine. Remember, just as we have talked about this heat engine here, we can also talk about the refrigerator. See here, रेफ्रिजरेटर के बारे में हम देख सकते हैं कि रेफ्रिजरेटर का काम क्या होता है. देखो, सपोज दिस इज द रेफ्रिजरेटर, then it will extract the amount of heat Q2 from the cold system. तो T2 टेम्परेचर पे जो सिस्टम रहेगा, उसमें से ये Q2 अमाउंट ऑफ हीट एक्सट्रैक्ट करेगा. उसके लिए उसको वर्क डन करना पड़ेगा, W इतना वर्क डन उसके लिए लगेगा, ठीक है. एंड देन combined part Q1 Q2 plus W, the combined together will be rejected to the surroundings here, which is going to be at a higher temperature T1. So Q1 amount of heat is going to be rejected to the surroundings, which consists of W as well as Q2 here. So इसका जो डायग्राम है वो ऐसे कुछ बनेगा. देखो, W यहाँ पे कंबाइन होने जा रहा है, और एट द सेम टाइम Q2 भी यहाँ पे कंबाइन होने जा रहा है. So Q2 and W2 becomes or get combined and becomes Q1 here. So therefore we can say that the equation is once again the same here, that is Q1 is equal to W plus Q2, or we can simply say W plus Q2 equal to Q1, which gives that W is equal to Q1 minus Q2 here. So W is equal to Q1 minus Q2, and the coefficient of performance here in case of refrigerator will be denoted by alpha, and it will be defined as. तो यहाँ पे coefficient of performance कैसे डिफाइन किया जाता है, क्योंकि देखो, जब हम रेफ्रिजरेटर यूज करते हैं तो उसमें वर्क डन जो हम करते हैं वो बन जाता है इनपुट. ये वर्क डन जो हमको करना पड़ता है वही यहाँ पे इनपुट बनने वाला है, और जितना अमाउंट ऑफ हीट रेफ्रिजरेटर सक्सेसफुली अंदर वाले लो टेम्परेचर वाले सब्सटेंस में से सक्सेसफुली निकाल पाता है, वो हमारे लिए आउटपुट बन जाता है. ये हो गया आउटपुट. और efficiency मतलब क्या होता है, आउटपुट अपॉन इनपुट. So also so therefore we can say that this output is Q2 here and input is going to be W here. So therefore the formula for efficiency or coefficient of performance in case of the refrigerator is simply Q2 upon W. But since W is going to be Q1 minus Q2, we can say alpha can be written as Q2 upon Q1 minus Q2. And again we can just replace this Q1 and Q2 by T1 and T2, that is the temperatures of sink and system or source. So we can say that this Q2 will be replaced by T2 and Q1 will be replaced by T1 minus T2 as it is, which also can be written as, so इसको हम ऐसा भी लिख सकते हैं 1 upon, देखो alpha can be written as, if we divide this whole thing by T2 here, then we can call it as T1 upon T1 upon T2 minus 1. Okay, so this is replaced here. Main thing is that here in both of these equations, जो ईटा का जो इक्वेशन था कोएफिशिएंट ऑफ एफिशिएंसी का, तो उसके लिए हमने देखा 1 माइनस T2 अपॉन T1 हुआ करता है, बराबर. और ये T2 अपॉन T1 या T1 अपॉन T2 ये जो वैल्यूज है, तो ये इनमें कॉमन है. तो अगर हमको इन दोनों के बीच में रिलेशनशिप अगर डिराइव करना है तो सिंपली क्या करो, तो यहाँ पे अगर T1 से अगर हमने डिवाइड कर दिया इस पूरे इक्वेशन को, ये वाले इक्वेशन को ना, अगर T1 से डिवाइड करते हो, न्यूमरेटर डिनोमिनेटर बोथ डिवाइड बाय T1, तो क्या बनेगा? देखो, अल्फा विल एक्चुअली बी इक्वल टू T2 upon T1 divided by, here it will be actually T1 upon T1 is 1 only, minus here it will be T2 upon T1 again. But as we know that this T2 upon T1 can be obtained using this equation. So T2 upon T1 is nothing but 1 minus eta. So if we replace this T2 upon T1 by 1 minus eta here, then we can get the relationship between eta and alpha. That is T2 upon T1 is replaced by 1 minus eta divided by 1 minus T2 upon T1, which is again 1 minus eta. So if we just simplify this further, this 1 minus 1 plus eta, 1 gets cancelled, and we are left with alpha is equal to 1 minus eta upon eta. And also we can replace or express eta as alpha is equal to 1 upon eta minus 1. Okay, so ये relationship है इन दोनों के बीच में, याद रखो इसको ठीक से. And here always remember that alpha is going to be greater than 1, not like efficiency, it is always less than 1. अल्फा का जो वैल्यू है, ये देखो यहाँ पे अल्फा इज eta is going to be less than 1, so 1 minus eta will be also less than 1, and this eta will also be less than 1. so इसलिए less than 1 नंबर का जो रेशियो है, तो वो अल्फा से 1 से बड़ा भी हो सकता है, 1 से छोटा भी हो सकता है, doesn't matter. So here we have to understand correctly. So this is all about the coefficient of performance of a refrigerator. And as we have already studied in case of the Carnot cycle, Carnot cycle is the simplest or simplest machine which has a very efficiency, which has efficiency very close to 1, you know, which is a cyclic process. In that, the first process or first part of that process is nothing but a isothermal expansion of a gas. Remember, this is the first part, which is the isothermal expansion. तो यहाँ से A से लेके B तक isothermal expansion हुआ करता है, and further from B to C adiabatic expansion takes place like this, and then from C to D the isothermal compression takes place like this, and after as the last part from D to A the adiabatic compression takes place. तो देखो यहाँ पे इस पूरे ग्राफ को अगर केयरफुली अगर नोट करते हो ठीक से, तो पता चलता है कि देयर आर 2 compressions and there are 2 expansions also. So let us see, this curve is a isothermal curve. Okay, this curve is going to be the adiabatic one. Okay, this curve is going to be isothermal again, but it is a compression as the volume is going to decrease. यहाँ पे volume है, हाँ? This is the volume plotted here. Okay, and suppose that this is the pressure here. तो pressure हमने यहाँ पे plot किया हुआ है, ठीक है. तो जब हम A से B तक जाते हैं तो volume increase होता है, मतलब it's expansion. Again when we go from B to C, volume increases, so it's again an expansion. But what is the difference between the two? This is an isothermal expansion and this is a adiabatic expansion. And when we move from C to D here, it is going to be the isothermal compression, because volume is going to get decreased, right? And even D to A, again the volume is going to decrease further, and that's why that is also compression, but that is adiabatic compression. तो देखो, 2 adiabatic curves है, 2 isothermal curves है. अभी हमको ये पता है ऑलरेडी कि आइसोथर्मल कर्व के अंदर जो वर्क डन होता है, तो वो उसके नीचे का एरिया के बराबर होता है, तो वो हम निकाल सकते हैं आराम से. और यहाँ पे भी इस प्रोसेस में भी जो वर्क डन होगा वो भी उसके नीचे के एरिया के बराबर होगा, बिल्कुल. और यहाँ पे हम देख सकते हैं कि इस BC कर्व के नीचे का जो एरिया है, तो वो BC के मतलब एडियाबेटिक के अंदर किया हुआ वर्क डन रहेगा, और इस कर्व के नीचे का जो एरिया है वो उस प्रोसेस के अंदर किया हुआ वर्क डन रहेगा. और अगर हम देखेंगे पूरा नेट वर्क डन जो है, नेट वर्क डन, मतलब ओवरऑल वर्क डन, क्योंकि यहाँ पे एक्सपेंशन के दौरान जो वर्क डन हुआ तो वो उसको हम बोलेंगे W1 which is going to be positive because there is expansion, and adiabatic work done, adiabatic process में जो भी वर्क डन हुआ तो उसको हम बोलेंगे W2 which is going to be again positive because it's expansion, and W3 is going to be the work done in isothermal compression but it's going to be negative, so this is W3. And here in the next step it is the W4 which is the adiabatic work done, W4 adiabatic compression के अंदर हुआ किया हुआ वर्क डन जो कि नेगेटिव होगा क्योंकि compression के अंदर है, तो ये W1 W2 minus W3 minus W4, this is actually going to be the net work done in the whole cycle, which is going to be actually the area of this cycle, no doubt. But if you see this from another point of view, then W1 के लिए क्या कौन सा फॉर्मूला हमको यूज करना जरूरी है? देखो ठीक से, W1 is nothing but the work done in case of cyclic process, isothermal process, and the temperature at that time is supposed to be T1 suppose. तो अगर T1 उसका टेम्परेचर उस समय रहा होगा तो उसमें हमको मिलेगा W1 is equal to nRT1 into log of V2 upon V1, करेक्ट है? नो डाउट. एंड दिस W2 हियर, W2 के लिए कौन सा फॉर्मूला हमको यूज करना पड़ेगा? तो हम जानते हैं ऑलरेडी W2 के लिए, अभी सपोज ये यहाँ पे T1 टेम्परेचर रहा है और यहाँ पे सपोज T2 इतना टेम्परेचर बन जाता है, तो W2 के लिए हमारे पास फॉर्मूला है NR इंटू, अभी यहाँ पे जबकि एडिमेटिक एक्सपांशन है तो वर्क डन इज गोइंग टू बी पॉजिटिव, सो वी कैन गेट दिस एज T1 minus T2 that is to be divided by gamma minus 1, no doubt. एंड W3 के लिए क्या हमको मिलेगा? देखो तो W3 के लिए वर्क डन मिलेगा हमारा, अभी देखो W3 मतलब आइसोथर्मल प्रोसेस के अंदर किया हुआ जो वर्क डन है जो कि T2 टेम्परेचर पे हुआ है, तो इसलिए W3 के लिए हमको मिलेगा nRT2 into log of, once again this V2 upon V1 comes out to be here. It can be proved that this V2 upon V1 is same as this V2 upon V1 here. And in short, in the next step is W4. Here, W4 is nothing but the work done in case of this fourth process. That is the adiabatic process, compression. तो compression के दौरान जो work done होता है, तो exact इतना ही होगा. Only it will be simply like this. And when we will just work out all these calculations here, so W2 and W4, if you can see carefully, W2 and W4 will just get cancelled. Why? Because they are exactly same but only opposite in sign. यहाँ पे माइनस साइन ले लो या यहाँ पे उल्टा कर दो उसको, एक ही बात है, नो डाउट. तो इसलिए in short we can say that this W2 and W4 is going to get cancelled and the overall work done is going to be actually W1 minus W3 only. तो यहाँ पे W1 minus W3 इतना ही हमको मिलने वाला है, और इसलिए हम बोल सकते हैं यहाँ पे कि ओवरऑल वर्क डन जो है तो वो कितना रहेगा? यहाँ पे देखो W1 is proportional to T1 and W3 is proportional to T2, so everything else will be taken common and we can say that this W is going to be proportional to T1 minus T2 here. So that's why, and Q1 जो है, Q1 मतलब क्या है? The amount of heat absorbed which is going to be proportional to T1, and just by taking the ratio here we can get the ratio of W to Q1 and get this simplified as T1 minus T2 upon T1, which is nothing but the efficiency of that Carnot engine, which is actually T1 minus T2 upon T1 as it is. So this is going to be the formula for efficiency of a Carnot heat engine, ideal heat engine, remember. Okay, so let us see now some MCQs based on this same. Okay, let us see the MCQ here. This is the same sheet we have solved the MCQs of kinetic theory of gases from. Now we just search for the MCQs on thermodynamics. Yes, just check here. In an isothermal expansion, gas has the volume of 96 gram of nitrogen at 27 degrees Celsius is increased from 70 liters to 140 liter. Okay, then the work done by the gas will be, okay, देखो ठीक से यहाँ पे 27 डिग्री सेल्सियस पे गैस रखा हुआ है और mass of gas is also given 96 gram. Okay, and isothermal expansion बोला है और ऑक्सीजन भी बोला है ना. ऑक्सीजन मतलब उसका मोलर मास तो हमको मिल जाएगा आराम से, तो उससे नंबर ऑफ मोल्स मिल जाएंगे देखो, and then we'll be able to calculate the work done. See here, isothermal expansion of oxygen. What do you, can you calculate the number of moles first? How much it is? Number of moles के लिए एक फॉर्मूला क्या होता है? It is simply the number of moles equal to mass upon molar mass, right? तो ऑक्सीजन का मोलर मास हमको ऑलरेडी पता है, so number of moles will actually be equal to mass upon molar mass. So mass is already 96 and to be divided by molar mass which is 32, so we get the number of moles as 3. Okay, तो number of moles तो मिल गया, चलो ठीक है. अभी आइसोथर्मल एक्सपेंशन बोला है तो वर्क डन के लिए क्या फॉर्मूला मिलेगा? nRT into log.
Sir.
Yes
Sir, 2 moles of oxygen.
how is it?
Sir, molar mass of oxygen is 16, na?
Molar mass of oxygen is 32. O2, don't forget, molar mass, not atomic mass. Okay,
Yes, sir.
atomic mass is 16. If we calculate molar mass, then it will be 32 actually, and we have to divide this 96 by 32. और अगर वैसे भी अगर 96 को 16 से भी अगर डिवाइड करेंगे तो भी क्या आएगा? 6 आएगा ना. 2 कहां से आएगा? ओके, तो yes, so formula is here, that is nRT into log of to the base e v2 upon v1, correct है? But as we know that this log of to the base e has to be converted into the log to the base 10, because in answer in options we want log to the base 10 here, right? So we can say that this 2.303 into nRT into log of v2 upon v1. But as we have given that the volume changes from 70 liters to 140 liters, what does it mean? V2 is going to be 140 and v1 is going to be 70. So the ratio of this 140 and 70 will be 2 in simply 2 to the base 10, and hence we can get this as W equal to 2.303 into n, which is 3, R which is to be kept as it is, and T must be replaced by temperature, which is given to be 27 degrees Celsius here. But don't forget again to convert it into Kelvin. So it will be 300 Kelvin here, and that is multiplied by log of 2 to the base 10, and hence when calculated here it becomes, okay, wait here, if we don't convert it into log to the base 10, then it will remain like this. तो यहाँ ऐसे ही रहेगा वो, और उस केस में हम यहाँ पे अगर n की वैल्यू डाल देंगे 3, r as it is, और t का वैल्यू भी हमारे पास ऑलरेडी 300, and that is multiplied by log of v2 upon v1 which is 2 to the base e. तो हमको मिलेगा 600 r log 2 to the base e. But again that is not the correct option.
Sir,
Yeah.
correct option will be D.
Yes. सुना नहीं दिया?
Sir, correct option will be D.
Yes, right. तो यहाँ पे ये 3 into 300 will become 900, and we can get this 2.303 approximately same as 2.3 into r into 900 into log of 2 to the base 10. Yes. Okay, just check. ये करो 16th वाला. A scientist says that the efficiency of a heat engine which operates at the source temperature 127 degrees Celsius and sink temperature 27 degrees Celsius is 26%. Then let us try to find out efficiency from the temperatures given here. What is the formula for efficiency? Already we have seen now. Eta is equal to 1 minus T2 upon T1. Correct hai? So if you just replace them here, then eta becomes equal to 1 minus T2. How much is T2 here? See, it is 27 degrees Celsius, which can be written as 300 in Kelvin, and 127 degrees Celsius, which is going to be 400 Kelvin. So 0, 0 cancel. We are left with 1 minus 3 by 4, matlab 1 by 4, which is going to be 25%. So the efficiency of that heat engine is going to be 25%. But he is saying that it's 26%. मैक्सिमम इफिशियंसी जो है, जो हमको मिल सकता है यहाँ पे, तो वो हमको 25% मिलने वाला है, उससे ज्यादा नहीं मिलेगा. तो he is saying whatever he is saying is not possible. मैक्सिमम इफिशियंसी का ये फॉर्मूला हमको मिलता है कैथोडिक से. इससे ज्यादा इफिशियंसी हमको कभी नहीं मिलेगा. इतना मिलता है हमको, वो भी कार्नोट हीट इंजन के को यूज करके. उससे ज्यादा कभी नहीं मिल सकता है. Yes, just check here this question number 30 here. Carnot heat engine operating between temperatures T1 and T2 has efficiency 1/6 when T2 is lowered by 62 Kelvin. Its efficiency increases to 1/3. Then what are the values of T1 and T2 respectively? So see here, फर्स्ट कंडीशन से हमको क्या मिलता है, देखो अगर वो T1 T2 इस दोनों टेम्परेचर्स के बीच में अगर वर्क कर रहा है और उसका एफिशिएंसी अगर 1/6 है, तो ईटा इज इक्वल टू 1 माइनस T2 अपॉन T1। ये फॉर्मूला यूज करके हमको क्या मिलना चाहिए, 1/6 इज इक्वल टू 1 माइनस T2 अपॉन T1 मिलना चाहिए, जिससे हमको मिलता है T2 अपॉन T1 इज इक्वल टू 1 माइनस 1 अपॉन 6। मतलब T2 upon T1 comes out to be, what is 1 minus 1 upon 6? It is 5/6, right? So this 5/6. ये equation number 1 हमको मिल गया, just for using the first condition. Okay. But if we use the second condition, which is given here, when T2 is lowered by 62 Kelvin, that means now in the different situation, T2 dash is going to be T2 minus 62। मतलब पहला वाला जो T2 था उससे 62 कम किया तो वो हमको T2 डैश मिल गया, नया T2 मतलब नया टेम्परेचर ऑफ सिंक। और T1 के बारे में कुछ बोला नहीं है, मतलब T1 is kept same, so T1 dash is going to be same as T1 only. So in that case, new efficiency, which is eta dash, will again be same, given by the same formula, that is 1 minus T2 dash upon T1 dash. But as we know that this efficiency, new efficiency obtained here is going to be 1/3, correct? So here eta dash can be replaced by 1/3, and here 1 minus T2 dash can be replaced by T2 minus 62, which is already given here, and T1 dash is to be replaced by T1 only. And just simplify this further and combine it with this equation number 1 here and get the answer. So if we just shuffle these terms, then ये पूरा टर्म इस तरफ उठा के लेके जाओ और इस 1/3 को उठा के उस तरफ लेके जाओ तो -1/3 बन जाएगा। तो हमको नेक्स्ट स्टेप में मिलेगा T2 minus 62 upon T1 becomes equal to 1 minus 1/3, that means 2/3। तो T2 minus 62 upon T1 is actually going to be 2/3, right? And hence we can say this, from this equation we can again get the value of, yes, we can just simplify this numerator and denominator and get this as T2 upon T1 minus 62 upon T1 is equal to 2/3. But as we have already proved the value of T2 upon T1 to be 5/6, so just use it here and get it as 5 upon 6 minus 62 upon T1 is equal to 2/3, so that if we shuffle these terms again, then we can get this 5/6 minus 2/3 is equal to 62 upon T1. Okay, from this we are going to get this T1 actually. Yes. So what is this cross multiplication here? So 3 5s are 15. 15 minus 6 2s are 12. So here it is going to be 15 minus 12 upon 18. एक्चुअली इसको ही हमको 2 से मल्टीप्लाई डिवाइड करना चाहिए था, तो 4/6, तो 5/6 माइनस 4/6 बिकम्स 1/6। वैसे भी यहाँ पे 3/18 आएगा, मतलब वो 1/6 ही बन रहा है एक तरह से। तो दिस इज गोइंग टू बी 62/T1। दैट मीन्स 3/18 is going to be 62/T1, means 1/6 is going to be 62/T1, means T1 must be equal to 62 into 6, which is actually going to be 6 2s are 12 and 36 plus 1 37, 372 Kelvin. This is T1 and
372.
yes, and T2 can be found out by the condition relationship between T1 and T2 here. Okay, so T2 will be actually 5/6 times of T1, where T1 is going to be 372. So if we divide this by 6, then we can get the 6 6 are 36 and 2. So 62 2s are 310, correct? So 310 Kelvin. So these are the two temperatures in which this heat engine operates between 372 Kelvin and 310 Kelvin, which is available in option number A here. Okay. Just check this 18th one. Question number 18. See, a thermodynamics process is shown in the figure. The pressure and volumes corresponding to the points in the figure are PA, PB, VA, and VD. given respectively, and in the process AB 600 joules of heat is added to the system. Okay, and in the process BC 200 joules of heat is added to the system. The change in internal energy of the system in the process AC will be. Okay, we have to do this carefully. See here. Just wait. I will use another board so as to crop this question. Yes. Okay. Now you can see here. Okay, can you read the question carefully? Yes. Let us try this question. The thermodynamic process is shown in the figure. Pressure and volumes at the corresponding points are given as figure follows. Okay, तो PA दिया हुआ है, PB दिया हुआ है, ओके, और VA मतलब इसका वॉल्यूम भी दिया हुआ है, और VD भी दिया हुआ है, मतलब यहाँ पे वॉल्यूम भी दिया हुआ है. ठीक है, तो ऐसे केस में देखो ठीक से हमको और ये भी दिया हुआ है कि द हीट इज एडेड टू द सिस्टम इन द प्रोसेस AB. तो A से लेके B तक, ये देखो ठीक से, ये सपोज हमने देखा, ओके, ये 4 पॉइंट्स है यहाँ पे. A, here it is B, here it is C and D. प्रेशर एंड वॉल्यूम कर्व इज गिवन हियर. तो ये जो वॉल्यूम है, A का वॉल्यूम वो कितना है यहाँ पे देखो, 2 × 10⁻³ मीटर क्यूब, राइट. So we'll just mark it here, 2 × 10⁻³ okay. And D का जो वॉल्यूम है, देखो D का वॉल्यूम दिया हुआ है यहाँ पे 5 into 10 to minus 3 मीटर क्यूब एंड प्रेशर जो है ए का प्रेशर दे रखा है 3 into 10 to 4 ओके एंड फॉरगेट अबाउट द यूनिट्स दे आर स्टैंडर्ड ओके एंड बी का जो प्रेशर है वो दे रखा है 8 into 10 to 4 राइट यस एंड नाउ विल सी द कैलकुलेशन इसमें देखो ए बी इस प्रोसेस के अंदर इन द प्रोसेस ए बी वी कैन से can you use the can you find out the work done in this process AB? We can call it as WAB. Chalega? WAB. Yes. So work done in case of AB is going to be 0. Why? Because the process AB is going to be a constant volume process, right? और वैसे भी देखो AB के नीचे कोई एरिया तो रहने वाला ही नहीं है. No area will be there in this below this curve AB, and that's why the work done in the process AB is going to be 0 because it is a isochoric process, and already we have seen that in case of isochoric process no work is to be done, right? That's why work done will be 0. Yes, and since the amount of heat added here is given to be 600 joules, देखो यहाँ पे क्या दिया हुआ है 600 of joules of heat is added to the system. That means Q dQAB, or you can say QAB, we'll say is going to be 600, and that is also positive because it is added to the system, right? And what about the change in internal energy in that case? Then if we use the इसको dW और dQ और du ऐसे सिंबल्स हम यूज करेंगे जो कि हमारे फर्स्ट लॉ ऑफ थर्मोडायनामिक्स के अंदर है. तो देखो यहाँ पे dW मिल गया, dQ भी मिल गया, तो du कितना होगा? du in case of AB will actually be dQ in case of AB minus dW in case of AB. करेक्ट है? यही तो है ना सेकेंड लॉ ऑफ फर्स्ट लॉ ऑफ थर्मोडायनामिक्स. तो चेंज इन इंटरनल एनर्जी in case of AB will actually be dQ, which is going to be 600 minus 0, which is going to be 600 only. Yes, give this as equation number 1, no doubt. चलो ठीक है, अभी हम आगे बढ़ेंगे. तो दूसरा क्या दिया हुआ है देखो यहाँ पे कि BC प्रोसेस के अंदर 200 जूल्स ऑफ हीट ऐड किया हुआ है. तो अभी फोकस करो इस BC प्रोसेस के ऊपर. So when the gas is taken from B to C here, some work is going to be done, right? Because it is the constant pressure process, right? BC here in the process BC we can say, okay? BC is going to be a constant pressure process, or we can call it as a isobaric process, okay? It is isobaric process. So in case of isobaric process, we know that the work done is going to be P into delta V. करेक्ट है? वर्क डन जो होता है तो वो P into delta V के बराबर हुआ करता है. तो इसलिए यहाँ पे हमको वर्क डन निकालने में आएगा. सो वर्क डन विल एक्चुअली बी इक्वल टू dW in case of BC will be P into delta V. But where is P? P is nothing but the pressure in that process. See here, what is the pressure, constant pressure in this process? It is 8 into 10 raised to minus 4, oh, sorry 4. Okay, so that is to be replaced here. So pressure के बदले यहाँ पे आ गया 8 into 10 raised to 4, and volume change मतलब V2 minus V1. तो V2 मतलब क्या? ये VD जो कि 5 into 10 raised to minus 3 दिया हुआ है यहाँ पे, और V1 मतलब ये VA which is 2 into 10 raised to minus 3 given here. So if we just subtract this 5 into 10 raised to minus 3 minus 2 into 10 raised to minus 3. So what we get here is yes, so we are going to get it as yes, 10 raised to minus 3 can be taken common, and we get this 8 into 10 raised to 4 multiplied by 5 minus 2 only left in the bracket into 10 raised to minus 3 out. Yes, so we get this as 8 into 5 minus 3. 5 minus 2 मतलब 3 ना, तो 8 into 3 बनता है 24, and 10 raised to 4 minus 3 becomes 10 only. सो यहाँ पे ये बन रहा है 240 जूल. ओके, दिस इज द वर्क डन ओनली, बट ऑलरेडी इट इज गिवन हियर दैट in this process a 200 joules of heat is added. बराबर है. हेलो, हाँ सर बोलो. 12 से करा. हाँ हाँ ओके. हो ओके. हाँ हाँ हाँ. Okay, so here we can see that in the process BC 200 joules of heat is added actually, right? That we have to consider here. So इसलिए इस process में क्या होगा actually dqbc हमको निकालना पड़ेगा. What is dqbc here in this process? It is going to be 200, and that is also positive because it is added. Okay, again we can use the first law of thermodynamics and say that du in the process BC is going to be dq in the process BC minus dw in the process BC. ये पूरा BC का ही हम चल रहा है पूरा. तो dq कितना आया BC में 200 और dw कितना मिला हमको 240. करेक्ट है. So if we subtract this here, then we can get this as minus 40 joules here, right? And using this, we can say that is dubc is going to be minus 40 joules. So here we are going to get the change in internal energy in process BC, and here we are going to get the change in internal energy in the process AB. But here, see what we have asked here. तो देखो यहाँ पे हमको पूछा क्या है. We have to find out the change in internal energy in the process AC. Check. AC प्रोसेस के अंदर जो है इंटरनल एनर्जी कितना चेंज हुआ वो हमको निकालना है. एंड एज वी नो दैट द इंटरनल एनर्जी चेंज इज अ स्टेट फंक्शन. So whatever change in internal energy takes place in this AB and BC, if we add them together, then we are going to get the change in internal energy in the process of AC because it is a state function. State functions के बारे में ही हम ऐसा कर सकते हैं. तो देखो यहाँ पे ये जो DUAB है ये यहाँ पे मिला हुआ और DUBC जो यहाँ पे हमको मिला हुआ है, इन दोनों को अगर हम ऐड करेंगे ना तो हमको DUAC मिलेगा. तो देखो DU in process AC is actually going to be du in the process AB plus du in the process BC. Okay, because internal energy is a state function, we cannot use this as in case of work done. Work done के लिए ऐसा नहीं बोल सकते हैं कि dw in process AC is equal to dw in the process of AB plus dw in the process of BC. No, this is wrong. इवन dq के बारे में भी ऐसा नहीं बोल सकते हैं. dq in the process of AC is equal to dq in the process of AB plus dq in the process of BC.
They are path functions.
Yes, they are path functions, and that's why we cannot use this formally for the path functions here. We can use this only for the state function because it depends on initial state and final state. So that we can drop just this B here. ये B जो है तो वो drop होके यहाँ पे हमको A और C के बीच में का इंटरनल एनर्जी चेंज मिल जाएगा. सिर्फ इंटरनल एनर्जी के बारे में ही हम ऐसा कर सकते हैं, वर्क डन के बारे में और हीट एब्जॉर्ब के बारे में नहीं. इसलिए हमको यहाँ पे DUAC मिलने के लिए हमने क्या किया, ये DUAB निकाल के लिया जो कि यहाँ पे हमको मिला है. देखो यहाँ पे ये जो दिख रहा है ना 600 जूल, ये वही है. तो यहाँ पे हमको इसको डालना है. दिस इज 600 एंड हियर दिस DUBC भी हमने निकाल के रखा है. ये देखो इधर minus 40 जूल. तो वो अगर यहाँ पे डाल देंगे तो हमको मिलेगा DUAC which is to be found out. So here it is going to be 560 joule. So this is going to be the change in internal energy of the process. Okay, so just see the options. 560 A is correct option. Okay, समझा ठीक से. This is an important question actually. This has been asked in IEEE exam for some year, तो वो याद रखो ठीक से. तो इसमें हमने DQ और DW यूज करके DU निकाल के लिया दोनों प्रोसेस का, और उसके ऊपर हमने ये यूज किया स्टेट फंक्शन होने की वजह से एडिशन का प्रिंसिपल यूज किया. ओके, चलो ठीक है. लेट अस स्टॉप हियर. MHT-CET का पेपर जो है अनुष्का, इट इज ऑफ 200 मार्क्स एंड ऑफ 3 आवर्स. ओके, पीसीएम के लिए आपका 200 मार्क्स का पेपर होगा और 3 घंटे का पेपर होगा.